Hello, everyone. Today we're going to talk about entropy-learned hashing, constant time hashing with controllable uniformity. This is work I did with my co-authors Utku, Sirin, and my advisor Stratos, Idreos. So entropy-learned hashing is a project about hash functions, with hash functions appearing in many common data structures and algorithms, including hash tables, filter data structures such as Bloom filters, load balancing, sketches, dimensionality reduction, and in many other places. And in this talk in particular, we're going to focus on hash tables, although you can see in the paper results using similar techniques for filters and for load balancing. We focus on hash tables because they are a large part of the overall cost of systems. So for instance, at Google, they did a benchmarking study in 2018, finding that 2% of their total CPU usage at the company and 5% of their total memory usage at the company was in C++ hash tables. Translating this, using something like an estimate of 10 million servers for Google, this would be something like 200,000 machines at 100% utilization running C++ hash tables, or 200 zettabytes of total memory taken up in hash tables. And then it says, just in C++. Well, these are no longer exact numbers if we take into account the fact that Google uses hash tables in languages like Java and Python, Go, Rust, and many others. Maybe we can do something stupid and multiply by 5. And this gives us a rough estimate of something like 10% of the overall CPU usage of Google and 25% of the total memory usage in Google, just in the hash tables. And so our idea is going to be to try and make this more efficient through making better hash functions. And this similarly applies in many places inside databases. So you can see it inside of hash joins and OLAP databases, as well as in bit vector filters for filter predicate pushdown or Bloom filters inside LS entries, and in many other places. So to get to entropy-learned hashing, which is going to be about customizing hash functions to data sources, I want to talk about the traditional model for a hash function. In particular, the traditional model for a hash function is that if we feed in arbitrary inputs, we get uniform random outputs between 1 and m, where m is something that we decide and is usually dependent on our data structure. And if we get a second input, we assume the hash function gives us a second independent random uniform output between 1 and m. And in order to make this model happen, hash functions go through every single byte of the input data and perform some complex algebraic manipulations, with the end result that the designed hash functions we have nowadays fit our theoretical model of ideal randomness extremely well. And a simple question we're going to ask is what happens if we don't hash all of our input bytes? So what happens if we pre-process data and trying to decide in a smart way that we're only going to use certain bytes in the evaluation of our hash function? So to be more clear, we're going to select some subset of bytes to hash and feed only these bytes into the hash function. And as example, if we take Freddie Mercury, this character is making up his name, and we sample just bytes 2, 4, 6, and 10, we get the string EDER, and we feed just through the hash function. And similarly, if we get Beyonce Knowles and take just those bytes, we feed just those bytes through the hash function, with the idea that hashing costs are proportional to the number of bytes that you use, and therefore by using fewer bytes, we are making cheaper hash functions. The first thing I want to note is that if we have a large collection of items and we're sampling some bytes, if after sampling these bytes, the items are still unique enough, this recovers traditional hashing, right? If they're completely unique, this is exactly traditional hashing. And if they're mostly unique, we can show via equations later that the equations will be very similar to as if we hashed all bytes. And the questions we're going to attack are essentially which bytes should we choose, how many bytes should we choose, and how does this concretely translate to equations for our data structures. Overall, the major result that we're going to achieve is that we're going to take hash functions, which used to have their computation depend on the size of the key, and we're going to make the evaluation of those hash functions both cheaper and essentially independent of the size of the key. So that is, even as the size of our keys grow, we won't actually need to hash more bytes of those input keys. And this is going to produce large speedups in certain scenarios. So to model this problem, what we're going to think of ourselves as having is some collection of random variables. And these random variables arrive IID, and we're going to want to use this modeling to decide which bytes are going to produce the best results for feeding into a hash function. To do this, we're generally going to have 4 steps. The first is just going to be gathering some sample of past data. The second step is a set optimization procedure, which is going to pick the bytes which produce the least collisions from sampling on our training set. Step 3 then uses a separate validation set to estimate how this randomness applies to new data. So we're going to try and say, okay, even if we are basically building new hash tables from this data source, or if we have many insertions to our hash table, we still expect to see this many collisions from our sampling procedure. And then step 4 is going to be using the amount of randomness in those bytes to actually choose how many bytes are necessary for our hash function. So we'll start with step 2. So the thing we're going to optimize is we're going to try and choose for some set of bytes of size k, which bytes produce the fewest number of collisions. Or equivalently, we're going to optimize the collision entropy, which is defined as the negative log of the probability that 2 items drawn IID from our distribution are equal to one another. The idea behind this procedure comes from the optimization of Shannon entropy or traditional entropy, which is known to have essentially constant factor approximations to the optimal solution using this greedy procedure. And the idea is that iteratively, we choose the random variable that increases the joint entropy the most. So if we take a toy example of having training data, dog, cat, and rat, and we pick, say, the first byte of each item, this would produce 1 collision because both dog and dot share D as a first letter. If we pick the second byte, this is 2 collisions. And if we pick the third byte, this is 3 collisions. So the best byte is byte 1. After we fix byte 1, the next best byte to choose is byte 3, because this completely separates the training data. And you can see this is true even though individually byte 2 is better than byte 3 in terms of the number of collisions it produced. After conditioning on byte 1, byte 3 now adds the most to our joint randomness. And the idea is that we can apply this to a larger set of items, right? So we can essentially, if we had a much larger training set, we could still choose, say, bytes 51, and then 72, and then 43, and then 12, and then 4, and then ... iteratively picking the next byte that adds the most randomness on our training set. And then we finish this procedure when we've essentially separated out our entire training set. So this goes through step 2. Step 3 is then we want to estimate how many collisions we would likely see on new data. And the idea here is that we're going to take these increasing set of bytes that we've chosen. I should note in the previous example that this gave us solutions for choosing a single byte and then choosing 2 bytes and then choosing 3 bytes and so on. And we want for each set of size 1, 2, 3, 4, ... to estimate how many collisions we see on new items. To do this, we take our validation set and we essentially use a point estimator for the collision entropy. So that is, we're going to take the negative log of the observed number of collisions in our validation set over the possible number of collisions, which is the number of 2 combination of items from our validation set. And this gives us a point estimator for entropy, or for our collision entropy. And then we can essentially build confidence intervals around that using more complex solutions. So this is how we generalize to new data. And then finally, we want to use this amount of randomness to create hash functions for data structures. To do this, we need to understand how entropy in our sampling procedure translates to equations for data structures. So this will be essentially the expected number of comparisons for separate chaining hash tables. We also have it for linear probing hash tables in the paper. What we can see is that the thing on the left is just what we're defining. So this is the expected number of comparisons in a hash table lookup. This equation here is the same as for full key hashing and essentially depends on alpha, which is how full the hash table is. So that's the number of items over the number of slots in the hash table. And this term on the right is the penalty from doing partial key hashing instead of full key hashing. So this is essentially the added number of comparisons we expect to do in return for having this much faster hash function evaluation. And we can see that it exponentially drops off with increasing entropy, but also rises with the number of items that we're storing n. So how to use these equations to decide on how to build a hash function is that if we have some hash table, generally this hash table has a maximum capacity before it needs to rehash. So this is what happens in state-of-the-art linear probing hash tables, such as we see in practice. Given that there's a maximum capacity, so we have an upper bound on the value of n, we can use a decision rule that's something like, okay, we want no more than 0.1 extra comparison. And then using the capacity and decision rule, we can decide how many bytes to include in our hash function. So in this case, we would need only 2 bytes. If inserts cause the hash table to grow, so we change its capacity, then this also means that we have to rehash the items in the hash table. And this also gives us a chance to add more items to the hash table. We'll also note that this rehashing procedure allows us to regain robustness in case, for whatever reason, models drift, in case data distributions drift from the models we built. And the main idea is that on inserts, we can see how many collisions we expect to see because we know equations for hash tables. And then if we start observing things that are anomalous to the behavior we expect, we can switch back to more robust hashing. So that is, we can hash all the bytes. And this recovers good performance, even in case of workload drift. So this is a very brief overview of our overall end-to-end solution for building hash functions custom to the data set. I should also note that if we just want to build it for a fixed data set, we can just use steps 2 and 4 and not worry about step 3 of generalization. The other thing I should note is that this is generally taken from, I've generally presented this from a very theoretical point of view, but there are very many systems optimizations to make this much faster in practice so that it is faster than state-of-the-art hash functions. In particular, instead of single bytes, we generally choose words at a time. So, maybe the first 8 bytes are chosen. We use templated hash functions to generate this efficiently in C++ code. We have tweaks to the optimization to make branching more consistent inside a hash function evaluation. And then we have integration into the state-of-the-art base hash functions like XX hash or murmur hash or Y hash and so on. Overall, our results show first that for very large data sets, that this increase in asymptotic efficiency produces very large benefits. So for example, when looking up 8 kilobyte keys, such as you might see in deduplication of file blocks, this produces a 24x improvement in hash table lookups. For more medium-sized keys, which is going to be the focus of our experimental results, the gains are more moderate, but still quite consistent. So what we're going to do is compare Google's state-of-the-art hash table, Google Swiss table, and we're going to rip out their hash function and instead replace it with a custom hash function we're building. And what we see is across a range of different data sets that we're achieving much faster hash lookups. So in the graph, lower is better. And then the x-axis is showing us the number of different data sets that we're evaluating this technique on. In particular, we see it for IDs, 2 text data sets, and 2 URL data sets. These range from 20 to 130 bytes in length. And what we see is across all of them that entropy-learned hashing is consistently faster with a 1.9x faster speeds on average. In general, the larger the items of the keys is the data sets where this has greater benefit. So for instance, Wikipedia is the one where we have 130 byte length items on average, whereas wiki titles has 20 byte length items on average. So with that being said, this is entropy-learned hashing. We just saw that it has very great performance. The idea is also extremely intuitive and interpretable. So we're just going to hash some of the bytes. And we were able to regain robustness by falling back on full key hashing if data distributions changed. So overall, we had many benefits of faster hash function evaluation, provably nearly uniform outputs, and robustness via table rehashing. Thank you.